When someone is driving recklessly or otherwise moving very fast, they might be described as moving like a bat out of hell. But exactly how fast would a bat out of hell be? Our proximity to Halloween, objectively the best holiday, had me thinking about bats, and thinking about bats and Halloween led me to this colloquial phrase, bat outta hell. It's a phrase that's meant to imply someone is moving very fast, but I realized I didn't know just how fast bats could really move, or if they would move any faster given the assumed high temperatures and threat of flames in hell. So I hopped on Twitter and threw up the bat signal, hoping some experts would come to our aid, and we were lucky. Andrea Rummel, a PhD student at Brown University, and Dr. Teague O'Mara, an assistant professor at Southern Louisiana University, both agreed to share their knowledge of bat flight with us. So first, and most importantly, how fast can bats fly?
We don't really know very well. Flight is something that's really hard to study. We have a bunch of experts who are able to bring bats into a lab and put them in a wind tunnel that is basically like an air treadmill, and to get bats to fly within that. And so you can convince bats to do that for a while. Sometimes they play the game, sometimes they don't. The problem with those is that we can get bats to fly at the speeds that they really like, but getting them to fly really fast is hard. They just don't want to play the game. And like you're in a tube, you're flying out there, you're like, sure, it's fun and it's exercise because they just like to fly, but getting them to go really fast is hard. But in general, for animals, we have this sort of curved relationship in what they prefer to do, because it costs a lot of energy and it's really hard to fly very slowly. And it's because you're generating lots of lift. You have to push yourself up the ground. You have to beat your wings and create all that lift to keep you up. But if you fly really fast, then you have lots of drag. And so you have to overcome all of this drag on your body to be able to go really fast. And so we have usually these sort of hypothetical, and in many cases, true curve relationships where like animals have a sort of sweet spot. And for many bats, that's somewhere around 7 meters per second, between 5 and 8 meters per second. Our fastest bats that have been tracked are Mexican free-tailed bats in Texas, and they fly about 100 miles an hour. Yeah, and so these were radio tracked and they were followed with an airplane, and that's 100 miles per hour on the ground speed. We've modeled their airspeed, and it's a little bit slower, but not much slower than that, which is really fast because our Mexican free-tailed bats, I mean, they're only 10 centimeters long. They weigh 15 grams. So that's really fast for a little bat.
So ground speed, these bats can like put on the gas and like speed ahead at like 100 miles an hour. And that's the fastest recorded bat that we have. So if that's not a bat out of hell, I don't know what is. And these are also bats that are found in the like southern North America. So it's like the southwestern US through Mexico, Central America. So they're bats that live in warm habitats.
Dr. O'Mara also mentioned that other species of bats have been clocked diving into their home caves at speeds between 60 and 100 miles per hour in order to avoid predators like peregrine falcons, technically the fastest animals on Earth. So it sounds like we've got our maximum bat speed, but how might bat flight be changed in hell, where the temperatures are ostensibly higher than they are here on Earth?
Temperature is something that affects every living system, so there's like no escaping temperature. And the reason is that the underlying biochemistry, like everything that kind of powers life, it depends on temperature. So when you're warmer, those things move faster, and when you're slower, or when you're colder, those things move slower. And muscle is what makes us move, and muscle moves because of like underlying biochemistry. So muscle, just like everything else, is really temperature sensitive. And so what I've been working on is basically looking at how bat muscles are adapted to potentially low temperatures. And so it looks like some bat muscles are adapted to function better at low temperatures than we would expect based on kind of how poorly muscles do, how stiff our fingers get when it's cold. But then the other half of that, I guess, is that as you heat up a muscle, you generally expect to see increases in performance. But what it looks like is happening in bats is that there's kind of like a range of temperature, like a range of like degrees over which performance is possible. And so if you want to function better at lower temperatures, you have to shift that whole range downward. And so then that does compromise function at higher temperatures. And so in these bat muscles, it looks like to keep muscle speed and muscle power up at the low temperatures, that means that you compromise the stability of kind of the internal components of muscle at higher temperatures.
Okay, so making a bat's wings warmer might make it fly faster, but only up to a point. After temperatures get too high, the enzymes and other chemicals that make muscles work would start to break down, and the wings wouldn't work anymore. And depending on just how hot we think hell is, the poor bat might even get cooked before it could get away. So I always sort of assumed that the bat in question was trying to get out of hell fast because it didn't want to be there. So it would make sense for it to not be a native of hell or to have hell-adapted muscle functioning. But we have to know something about how bats respond to the danger of high heat or flames, right?
But whether or not they really want to get away from something hot or something cold, I'm not sure if people have used that. Those are like experiments that have been done with rats, for example, where you put a rat on a hot plate to see like how hot it has to be, and when do they start licking their paws, and how do they feel different kinds of stimuli. But we don't do that kind of stuff with bats. Maybe somebody has before, but I'm just not aware of it. People have been tracking bat responses to forest fires, not as they're like trying to get out of maybe a burning trunk, but how do they actually deal with the effects of things like smoke and heat? And they use that sort of physiological mechanism of torpor, and it puts them down into a really low state where they don't have to breathe. They don't have to really slow down their heartbeats, and sort of like they just shut things down as much as possible. And so they sort of treat fire events, if they're not in danger of flame, like maybe winter or something like that. Yeah, if it's actually on fire, they're going to get out. They're leaving, yeah.
That tracks. I'd want to get out of a forest pretty fast too if it was on fire. Oh, and Teague mentioned torpor. That's basically a state some animals can go into that dramatically lowers their metabolism and other bodily functions. I talked about torpor in my video on hibernation. But it's interesting to find out that not very much seems to be known about how bats respond to rather dramatic environmental stimuli like fire or extremely high temperatures. There's a cool direction for any of you future researchers out there. As I was speaking with Dr. O'Mara, I realized there was a logical next question in our sequence. Now that we know how fast bats can fly, how far can they fly?
It depends on the species a lot. So some bats will tend to like forage close to home, especially if they're looking for insects that sort of sit and they don't go very far. They'll forage close to home and they'll find a roost, and they'll maybe go 30 hectares, 20 hectares, if that. Those really long-range seed dispersers from Africa, Eidolon helvum, the straw-colored fruit bat, in the wet season when there's lots of fruit available, they'll fly about 35 kilometers from the roost. But in the dry season, when they've sort of switched over to look for nectar, they're flying up to 90 kilometers away. So they'll make a 180-kilometer round trip. And that's a little bit far, but we see that with some nectar-feeding bats in Mexico. So bats that are essential for keeping saguaros, and also agave. So bats are essential for tequila, though without them, we do not have that particular delicious beverage. So this nectar feeding bat in Mexico will fly also about 180 kilometers round trip a night. They'll congregate in maternity colonies where females all come and have their babies. And then they're flying out to cactus fields that are 90 kilometers away. So they go out, they fly out to feed on nectar, and then they come back to their babies. And they do that every night. It's just really spectacular what some of those animals do. So some stay close, some go far. Those free-tailed bats in Texas, they go very far.
You might have noticed that he mentioned several bats that are important pollinators or seed dispersers, including one bat that's important for reforestation in areas of Africa. While most of the bats people in North America might be familiar with are important for their ecosystems because they eat bugs, many other types of bats are important for their ecosystems too. And just like speed, it sounds like there's a lot of variation between species when it comes to how far bats will forage. So with all this variation in bat species, do we have a good idea of how bats and bat flight evolved?
It's super unclear because our earliest fossils bats look like bats. They look like a bat that you would find today, for the most part. They have a few extra things, like they have claws on the ends of all of their digits in their wings, but otherwise they look like a Vespertilia, an echolocating insect-eating bat that you find now. And these earliest bats are appearing somewhere on 50-ish million years ago. So they're very ancient, they're extremely old. and they just appear as bats. But so we don't really have fossil transitional bats. One of the reasons is that bats are very small. They lived in humid tropical places where it's hard to fossilize creatures. So that's a really difficult challenge for finding fossil bats. But we've had a number of really interesting molecular experiments to understand how you actually can sort of develop from a basal mammal, a basic mammal plan, like a mouse, how you can actually get to long fingers in a wing. And it really is a very simple sort of switching on of a regulatory gene that makes your fingers grow long. And if you keep it going, your fingers just keep getting longer and longer and longer, and it drags along a bunch of other kinds of things with it. So the process of getting to a bat is not that hard, or getting to a wing, let's say, getting to a wing, a handy wing, is not that difficult. We just don't see it in our ancient fossil record yet. Bats' wings are made up of their hands. And so most of their wing is their forearm. So it's their upper arm and their forearm. And then the big part that we think about at their wing is their hand. So it's their finger bones are all stretched out with a bunch of skin between those finger bones called a patagium. And it's super stretchy skin. It doesn't stretch the same way in both dimensions. It has a bunch of blood vessels and really weird and interesting muscles that are they're not anchored to bones. They're just floating in the wing, which is super cool. But those soft tissues don't fossilize very well. It's not like birds. We don't get Archaeopteryx with those beautiful wing prints because skin doesn't fossilize very well. We have very rare instances of fossilized skin and flesh. Like we find it occasionally, but it's not very common. Especially when you're talking about something that's only like 2 millimeters thick, not even. Bats sort of live at the energetic edge of what's possible for a mammal. They're like these crazy little things. Like mammals are not supposed to fly. And so when we take a mammal and throw it up in the air and let it go, we really see what the possibilities actually are and how flexible our anatomy, our physiology, and our social behavior really can be. Like bats sort of push the edge of what's possible. And I really think that by looking at those edges, we can learn a lot about what it just means to be an animal and what it means to be a participant in our biological world.
I could probably keep talking about and asking questions about bats for the next few hours. I just think they're such cool animals, and our guest experts today seem to think so too.
Bats are pretty outstanding creatures.
So I just think bats are really cool. They have cool arms. That's my favorite part of bats is their wings.
So I hope you've learned to love bats as much as we do, and maybe have a new appreciation for just how fast these little balls of fluff can fly. Do you have any questions about bats? What other Halloween adjacent subjects should I cover in the future? I'd love to hear your thoughts down in the comments. If you liked this video, don't forget to like it. If you didn't like this video, please share it with someone who would. And if you'd like to support the Roving Naturalist, remember to hit the subscribe button and the bell notification icon. Then go check out my Patreon page. You can also follow me on Twitter and Instagram. As always, thanks for watching, and I'll see you next time. Happy Halloween!